convenient if someone has his answer sheet.
So let's look at some more ideas out of Unit 1. And if you hear Miss Krause yelling at me, she's just complaining about something, as usual. So we'll just ignore that in the background as we look at inverse functions. So we're going to look at inverse functions three ways here. We're going to look at how to find an inverse algebraically, graphically, and tabularly, all through using one example, one f of x. So the f of x we're going to use for all three different methods is going to be x squared minus 4. So we're going to figure out how we can find f inverse of x using algebra, a graph, or a table. So one thing to remember is that this notation, the superscript -1 here on the f, that doesn't mean that it's an exponent. That just means it's the inverse of f of x. So let's look at the algebraic method first. So the way that I approach these is, in using a lot of algebra, I'll just replace the f of x with a y, because then it's going to involve less writing. Okay, so I'm just going to use y equals x squared minus 4. It's just an easier representation to kind of use when solving this algebraically. It's just less writing to use y instead of f of x. So now I want to find the inverse. This is the algebra method. The first step is you want to switch the places of x and y. So everywhere you see a y, you write down x, and everywhere you see an x, you write down a y. So this would become x equals y squared minus 4. Then to find the inverse equation, you have to resolve this for y. So I need to have the y isolated and everything else on the other side of the equation. So I'll start here by adding 4. So I get x plus 4 equals y squared. Square root both sides. Now since I square rooted both sides of the equation, I get plus or minus root x plus 4. So that is the inverse right there. Plus or minus root of x plus 4. So to write that in inverse notation, we would say f raised to the -1 of x, that just means f inverse of x, equals plus or minus root x plus 4. So again, I'm just replacing f of x with y just so it's less clunky when I'm switching x and y and then solving this out, but I want to write it in proper notation, so I'll always take that and write my answer as f inverse of x equals, and then whatever it happens to equal. Excellent, so I've found the inverse using algebra. Now how could I use a table? Well, let's make a table for f of x here. So here's my table for f of x. I'm going to plug in just some convenient, easy values for x. How about -2, -1, 0, 1, and 2? I plug those in, I get 0, -3, -4, -3, and 0. Okay, so that's a little partial table for f of x. So let's say I wanted to make a table for x, comma, f inverse of x. Well, the way that you would do that is you would just switch the x and the f of x columns. So down the x column, I'm literally going to write what I had in the previous f of x column. So 0, -3, -4, -3, and 0. And in the f inverse column, now I'm just going to write what I had for my x values before. -2, -1, 0, 1, 2. So I'm literally just taking the x and the y values and switching them. And that gives me a table for the inverse function. So that's how you can quickly take an original function and use the table to create a table for the inverse. So how could we do this with a graph of f of x? Okay, so I'm going to sketch the graph of f of x. It's a parabola. Vertex is at 0, -4. And it's got a 0 at 2, 0. And -2, 0. So there's a sketch of the graph, and I'm just labeling a couple of the points. So that's the graph of f of x. So how could I quickly create a graph of f inverse of x? Well, there's kind of two ways to think about this on the graph. I could think about this as the definition of an inverse function, or an inverse function or relation, in this case, because f inverse here is actually going to be a relation, not a function. We'll see why in a minute. So that definition graphically is that I can create the inverse by reflecting the graph over the line y equals x. So I can consider the line y equals x to be like a mirror, and I could reflect the points kind of diagonally across that line. Now in this case, I think that's going to be hard to do because I've got points kind of that lie on both sides of the line. So thinking about that like a reflection might be challenging depending on just how good your geometrical skills are, just kind of estimating where points would be when you reflect them. But you could try that. Or we could think about this kind of like how the method we used with the table, and we could just take a couple of points on the graph and just interchange the x and the y parts of the coordinates. So 0, -4 would move to -4, 0. -2, 0 would move to 0, -2. And 2, 0 would move to 0, 2. So we would have, that is the graph of f inverse of x. Now notice that f of x, the parabola, f of x is definitely a function. And this is easiest to see with the graph. I mean, it passes the vertical line test. For each x, there's only one y value that pairs up with it. But when you look at the inverse, you can quickly tell it fails the vertical line test an infinite number of times. It's not a function. It's a relation. So f inverse of x, not a function. F inverse of x is a relation. A relation just being, it's a collection of x values and y values. It has a graph, but it fails the vertical line test. So notice there are certain x values that have multiple y values that pair up with them. So I've drawn this, so there's an example that's already marked on the graph and on the table. So look at the table and the graph. The points 0, 2, and 0, -2. That's the same x value, circling it in the table. So the x value for both those points is 0, but they both have different y values. So here you have one x value that's pairing up with multiple y values. That makes f inverse not a function. So hopefully that was a decent review of finding an inverse using